Hello and welcome to Module 2, Systems Engineering Process Models, Concepts, Stakeholders, Problem Statement, and Requirements. In this component, we will talk about elaborate conceptual design, problem statement formulation, stakeholders, and feasibility analysis. Conceptual system design is first and foremost the most important phase of system design and development process. This comes early on in the lifecycle activity and is very critical upfront in establishing the commitment to form, fit, function, cost, and development of the development cycle. This establishes everything else and sets the tone for all the downfield stakeholders and subcomponents as the system progresses. So that's why this is the very most critical element of systems engineering and in the system design lifecycle process. In this phase, the systems engineering is responsible for taking the lead in defining the problem and doing the advanced planning, concepts, and feasibility analysis. Lastly on here, you see the ilities. In upfront, you may have to think about things such as reliability, maintainability, supportability, and human factors or ergonomic types of things. Those are things that will come into play much later on in the system, but if you haven't designed for them and planned for them up front, you'll run into issues later on. This chart from the Blanchard and Fabricki text explains the life cycle commitment. At the very bottom, you'll see the conceptual, preliminary design, detailed design, development, construction, production, and then system use. So it takes you through development, through deployment, and eventually disposal, moving from left to right. The graphs in each show the commitment to each of these elements. So the first one in there will select the ease of change. You see very up in the very beginning, it's almost 100%. It's in the concept phase, it's very easy to make changes to the system at that stage. The further on you get into the project, the less you are able to make changes, especially once you get out of the conceptual design process. When you get out of concept and you get into the detailed design, then it gets much more difficult, and then by the time you get into actually deploying it, it's very difficult to make changes. Conversely, you look at the system-specific knowledge. At the very beginning, you don't have system-specific knowledge because you're in concept and you don't know a lot of those things. At the same time, you haven't put a lot of cost into it, so the cost is very low. In that conceptual design component, that's where you can make all those changes and your costs and everything that you have invested into the system are very minimal. Once you get out of that phase into the design and development phase, you notice that the radically changes in the graph. The ease of change is now gone from 100% to 50% and will soon be 25, whereas the investments in terms of cost and then the knowledge that you have acquired have only started to slowly creep up. By the time those system-specific knowledge has really creeped up and gotten high, you're in the end stages of the system and you're very difficult to make changes. This graph illustrates how critical it is to make these decisions upfront in the conceptual preliminary design component of the system. If you don't, you may not realize it until 2 or 3 cycles later on, at which point it's much more difficult to make changes and your system is much more established and it is what it is. Because of the nature of how critical that upfront systems work is in the conceptual system design phase, that is where systems engineering discipline has the most influence and the most ability to make the system successful. Their influence up front is very critical, and the influence of the design disciplines or the subject matter experts, the sub-engineers working on subcomponents, are not nearly as influential in the conceptual stage because they're still learning, they haven't defined what it is that they're going to be. As you get into development and deployment, those eventually cross paths. The influence of the systems engineer becomes much less, and the influence of the sub specialties becomes greater. That's because the system is defined properly up front. There shouldn't need to be as much work on the back end in order to manage it. Going back to the Blanchard and Fabricki diagram 2.4, we're going to take a look at the specific steps within conceptual design. The first step in that conceptual design is even identifying what exactly is the problem. In order to do that, you need a problem statement. John Dewey is a philosopher who said that a problem well stated is half solved. And what he means by that is that you have to step back and make sure that you all agree on what exactly is the problem before you go and try to solve it. Albert Einstein gave a quote once. He was asked, if you only have 1 hour to save the world, how would you spend that hour? And he said, I would spend 55 minutes defining the problem and 5 minutes solving it. That line of thinking is very contrary to how people operate in business today or even in personal lives. People want to jump right to solutioning and fixing a problem before they truly even understand what the problem is. Instead of going and defining exactly what they think the intended solution is, you should step back and make sure you truly understand the problem so that you can make sure that the solution fixes the need as opposed to what the perceived intent should be. So for example, in 2002, a flood washed out a bridge across the Santa Cruz River near Tucson, Arizona. This made it very difficult for Native Americans in Mission San Xavier Dabac to get to the Bureau of American Indian Affairs Health Center. Their problem statement included a preconceived solution. They said, we must rebuild the bridge across the Santa Cruz River. By doing so, that pigeonholes you into a solution saying, we have to have a bridge. Now, step back. You used to have a bridge. There is no bridge anymore. You have to get across the water. Logic says we need a bridge. And so if their problem is we don't have a bridge to get across there, the only solution that they can really do is to go and put in a new bridge. While it doesn't seem like that's much of an issue, that does lock them in and doesn't give them other ways to creatively address the issue. So if you think about it, what truly is their need? Is their need that they don't have a bridge, or is their need that they need to be able to get across the way? The problem statement, a better way of looking at it, would say the Indians at the mission do not have a convenient way to get to health care. They need a way to obtain medical assistance. That truly is the underlying need behind it. That's why the bridge was there. The bridge was an original solution to solve the need. Not having the bridge wasn't the problem. Not having the solution to the problem brought out the original problem. So in this case, if you said something other than just need a new bridge, you could move the health center to the other side of the river. You could have a watercraft. You could have aircraft. You could train in-home providers, or you could rebuild the bridge. You could rebuild the bridge. That is one potential solution. There are many other ways that you could solve this problem. You could train people. You could train doctors and staff within the community. There's numerous ways to solve the problem. But if you go in and you imply a problem or imply the solution, that is a very narrow scope in there. Frequently, people will do this within business. They'll try to even say it as lack of or need more. So lack of training is the problem. Lack of performance standards. Well, lack of performance standards is another way of saying we need to go and create this solution. Realize too that when somebody says lack of, need more, they're applying a solution and say step back, truly understand what exactly is the problem that you're trying to solve. Perhaps the solution that they are implying is the one that you might want to go with, but at the very least, you need to do the due diligence to make sure that it is the most robust option available. Another example here is a preconceived solution of needing a stapler. If you say, I have papers, I'm taking them to a meeting, I need to staple them together. Instead, you should look at the top level function definition, which is the system should hold together 2 to 20 pieces of 8.5 by 11 inch 20-pound paper. What other ways could you do that? You could staple it, you could paper clip it, you could fold around the corner, you could put pages in a folder. There are many different ways to solve the same problem without having the exact stapler. Moving into conceptual design, the next piece is to analyze the stakeholders. Stakeholder is defined as somebody who has tangential responsibility or interest within the system. They could be a customer or an internal customer of the system. They could be somebody who's a supplier, or they could have somebody who has a vested interest or of an interdependent element of the system. So take the example of the Uberless driver. So first you have to define who is the stakeholder within the Uberless driver. In theory, you think, well, there is no stakeholder. It's a car. There is no driver. So since there's no driver, there's no stakeholder. In actuality, that's very short-sighted because there are numerous stakeholders. The end customer is still a passenger or paying customer, so somebody who could do it. Somebody who could be traveling in it. It could be the transport owner. It could be somebody who is an internal customer of technologies or the development team. It could be a regulatory agency because we know that if Uber is going or somebody else is going to create driverless vehicles, there will be some regulations that come through it. Sponsors, maintainers, operators, stockholders, bystanders, somebody standing on the street corner as a car is driving by, somebody driving down the street with a driverless car going next to them. They certainly have a vested interest in them. So I'm not going to go through all these in here, but you understand that the concept of a stakeholder is very broad. It's not nearly as narrow as you would initially think, and you can't look at it in just a very straightforward method. If in doubt, if you think somebody might be a stakeholder, they probably are. So now consider the system feasibility analysis. When you start looking at system feasibility, you have to look at 3 steps. And the first step is to identify the possible system level design approaches. So this could be different technologies, maturity, type of technology, stability and growth potential, anticipated technology life, and then the number of supplier sources. So what are the potential options available? And of course, again, feasibility, you're just analyzing, is this something that we can even do? Is this something that's even possible? So what are the different technologies available? Is there something new? Is there something in development? A lot of times this feasibility analysis comes because somebody says, hey, here's a great new technology. How does this work? So you might have a different technology, but you might look and say, are there different ways of accomplishing the same goal? Stability and growth potential. Is there an untapped market? Is there something that doesn't exist today? Second step is to evaluate the most likely approaches in terms of performance, effectiveness, maintenance, logistics support, and economics, and whatnot. So first of all, how could you go about and accomplish this? Performance, what level of performance could you expect? How effective could you expect it to be? A lot of times you may need to do some piloting or some sort of testing therein just to have some feasibility of, is this something that could work, or even just the basic proof of concept. Those first 3, the performance, effectiveness, and maintenance, are common complaints by consumers about how a new system or new technology may have gone. This is oftentimes a result in poor feasibility analysis up front, whereas the systems engineering function did not truly understand what the level of performance that could be expected, or how it could be maintained, or how effective the final solution would be. And then the third step would be to recommend the preferred course or courses of action. So how is it producible? Is it supportable? Is it disposable? Is it maintainable? And then what are the expected lifecycle costs? Even in just the basic feasibility analysis, when you take a design, you have to look at the manufacturing or production elements of it and say, is this something that could be mass produced, or would this have a whole lot of issues that came about with it? Is it something that could be serviced and support? Is there a way that, is it a virtual thing? If it's a technology, is it a way that we could integrate it in with existing systems? Is there a way that we could communicate it? If it's a physical system, is there a way that we can go and physically support it and provide the maintenance that it needs to have? Disposability, once it's done with this life cycle, what happens with it, especially if it's a high cost item or if it's got materials or things like that that need to be transferred or recycled. And then life cycle costs. Obviously, just in the overall feasibility, what is the overall expected life cycle costs? In a car, for example, you look at the upfront sticker price, and then maybe maintenance and gas and that sort of thing. But what else comes with that? Well, there's insurance, there's eventual salvage value when you go and you trade in that vehicle. All those things are what are the overall life cycle costs that truly impact the end consumer. Those are all 3 steps that need to be done in order to complete a successful feasibility analysis.